Close your eyes for a moment. Imagine standing under a sky with no city lights. For thousands of years, that sky looked like a perfect machine. Planets moved, galaxies turned, gravity held the clockwork together. But when modern telescopes looked deeper, the machine began to stutter. The outer stars of galaxies moved too fast, the universe expanded too quickly, and two cosmic rulers gave two different answers. It did not look like one small error, it looked like a crime scene. The first clue was dark matter, the second was dark energy, the third was the Hubble tension. Three shadows in one cosmic model. The standard interpretation is not foolish. It is powerful, precise, and deeply successful. But it also asks us to accept something strange. Most of the universe is known through what it does, not through what it is. PTQ begins with a different question. What if the universe is not missing pieces? What if the board underneath the puzzle is bent? What if the darkness is not a hidden substance, but the residue of projection? This is not a claim that dark matter has been disproven. It is not a claim that dark energy is fake. It is a more dangerous question. If physical reality is a projected slice of a deeper geometry, then what would projection leave behind? And could those leftovers be visible at the largest scales of the universe? The first shadow is dark matter. Imagine a carousel spinning too fast. If the central pole is weak, the horses near the edge should fly outward. A spiral galaxy has a similar problem. The stars near the outer rim move so quickly that the visible stars and gas do not seem to provide enough gravity to hold them. And yet, the galaxy does not fly apart. So the mainstream interpretation is simple and powerful. There must be additional mass we cannot see, a dark halo, invisible to light, visible only through gravity. The second shadow is dark energy. The universe is not merely expanding, its expansion appears to be accelerating. To describe that acceleration, cosmology introduces a dark component that changes the expansion history of space itself. The third shadow is the Hubble tension. One method looks back to the early universe, using the fossil light left behind after the Big Bang. Another method looks at the late universe, using nearby distance ladders and exploding stars. Both are measuring the expansion of the same cosmos. But the answers do not perfectly agree. One cosmic ruler points lower, another points higher, and the disagreement has refused to disappear. This is where the puzzle metaphor becomes useful. The standard model sees gaps in the picture and introduces invisible pieces to complete it. Dark matter fills one gap, dark energy fills another. New physics or hidden systematics may fill the crack between early and late measurements. That is a reasonable scientific move. But PTQ asks us to look under the puzzle. Maybe the pieces are not missing. Maybe the board is not flat. If the surface beneath the puzzle is lifted, the picture will look distorted even when every piece is present. In PTQ, that lifted board is geometry, and the distortion is residue. Not a new particle, not a fluid, not a force added by hand. A geometric effective effect, a leftover trace of projection. Imagine a dark room. A hand casts the shadow of a rabbit onto a wall, but beside the rabbit's ear there is a strange bump. One interpretation is that something is stuck to the wall, a hidden object, an invisible lump, something extra. But another interpretation is possible. The wall may be clean. The bump may come from the shape of the hand, from the angle of the light, from the structure of the object being projected. PTQ uses this second logic. The anomaly may not live inside the wall. It may come from the act of projection. In the language of PTQ, the observed world is not the full structure. It is a projected physical sector, and projection is not free. When a deeper geometry is forced into an observable slice, some part of the original structure cannot be perfectly erased. That remainder appears as residue. The cleanest place to test this idea is the galaxy rotation curve. A galaxy is not just a beautiful spiral, it is a dynamical test bench. Every star moving around the center is a clock. Every orbit is a measurement of gravity. In the outer regions of galaxies, gravity is extremely weak. That is where a small geometric residue would be easiest to notice. If the residue slightly changes the effective gravitational response in weak fields, then the outer stars may move faster without requiring a separately tuned dark halo for every galaxy. But this is also where the idea becomes vulnerable. PTQ cannot simply explain one galaxy. That would be too easy. It must face many galaxies, different sizes, different masses, different gas fractions, different brightness profiles, and the same residue structure must keep working. If every galaxy needs a different patch, the theory fails. The real test is not whether one rotation curve can be fitted. The real test is whether one geometric rule can leave the same kind of fingerprint across many cosmic systems. That is why galaxy rotation is not only a mystery, it is a laboratory. The Hubble tension is a different kind of test. It is not about one galaxy. It is about how the universe is read across time. Early universe measurements look at a cosmic screen when it was dense, hot, and tightly encoded. Late universe measurements look at a screen that has stretched for billions of years. Now imagine projecting the same image onto an elastic fabric. When the fabric is compact, the distortion has one pattern. When the fabric is stretched, the distortion changes. The image is not fake in either case, but the screen has evolved. This is the PTQ possibility. Early and late measurements may both be reading real projection effects, but through different states of the same cosmic geometry. Not a random error, not magic, not a license to move the goalposts. A systematic residue, if it exists, must be governed by one rule. It must connect early geometry, late geometry, and the observable sector. That is why the Hubble tension becomes so important. For PTQ, it is not only a problem, it is a pressure test. But now the theory reaches its most dangerous gate: gravitational waves. If space is a road, gravity waves are signals racing across it. If a theory adds bumps everywhere on that road, the signal should slow down, speed up, or scatter. But in 2017, a neutron-star merger sent both light and gravitational waves across the universe. They arrived almost together. That event placed a brutal constraint on any theory that modifies gravity. Do not casually change the speed of gravitational waves. For PTQ, this is not optional. The residue cannot disturb the tensor sector, the part of geometry that carries gravitational waves. It must act, if it acts at all, in trace-like or scalar-like sectors. A better image is the ocean. The residue may change the background density of the water, but it must not change how the surface wave travels. That is the tightrope. Modify the cosmic background, leave the gravitational wave untouched. Fail here, and the theory does not survive. This is what makes PTQ both beautiful and fragile. It is not allowed to win by adding patches. If the galaxy scale needs one residue, and cosmic expansion needs another, and gravitational waves require a third exception, the framework collapses. That is the romance and the cruelty of a unified theory. One rule must survive every scale. Quantum probability, galaxy rotation, cosmic expansion, gravitational waves. If one scale refuses the rule, the theory dies. But if the same fingerprint appears again and again, then the anomalies may not be separate mysteries. They may be different shadows of one projection. So what are dark matter, dark energy, and the Hubble tension? In mainstream cosmology, they remain profound open problems. In PTQ, they become a map, not proof, not a solved case. A map of where projection residue might reveal itself. On galaxy rotation curves, in the expansion history, in the disagreement between cosmic rulers, at the gate guarded by gravitational waves. The universe may not be broken. It may not even be missing something. It may be leaving fingerprints. And if those fingerprints follow one rule, then the darkness may not be empty. It may be geometry seen from the wrong side of the projection. What we call anomaly may be the universe whispering, "You are not seeing the whole structure."